SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning, and today we will discuss the vapor compression cycle. In this lecture, we will cover the reciprocating compressor, work in reciprocating compressor, volumetric efficiency of reciprocating compressor, in addition to the analysis on vapor compression cycle. In vapor compression cycle of refrigeration, instead of using ideal gas equations, we will be using charts and tables in order to find the properties of vapor at different states. In vapor compression cycle, if you look at the Carnot cycle on temperature entropy diagram, in vapor compression cycle, the heat addition and heat rejection, let us start 1, 2, 3, 4. Heat addition and heat rejection, this is QL and this is QH. It takes place during boiling and condensation of refrigerant. So, process 2 to 3 is nothing but the condensation of refrigerant, and process 4 to 1 is nothing but boiling of refrigerant at respective temperature T1 and T2. In these type of machines, the compression process is very important, and in this type of compression we cannot use this formula, right. So, and most of the vapor compression refrigeration system, reciprocating compressors are used. So, the analysis of reciprocating compressor with reference to the vapor compression systems become important. A reciprocating compressor works on slider crank mechanism. A slider crank mechanism is a 4-link mechanism consisting of a piston, a sliding link connected to a rotating link which is known as crank, and there is a connecting rod. This rotational motion of crank is converted to the reciprocating motion of the piston. Most of the applications in vapor compression system, it is a vertical type of system. So, there is a crankcase and a cylinder, and piston is fitted inside the cylinder. So, when the crank rotates with a certain RPM, to and fro motion of the piston takes place. There are two positions, that is top dead center and bottom dead center, where the direction of the movement of the piston, the change in the direction of the movement of the piston takes place, and this length is known as stroke of the compressor. Now, if we draw this on PV diagram, starting from state 1, when the piston is at bottom dead center, compression takes place, and this compression process is a polytropic compression process, state 1, state 2 and state 3. Now, in this process, part of the process is isentropic, sorry, not isentropic, polytropic, PV raised to power n is equal to constant, and part of the process is constant pressure process. What happens? I will draw a larger diagram. What happens when the piston moves in upward direction? The system behaves as a closed system. It has two valves, this compressor has two valves. Initially both the valves are closed. So, when compression takes place, it follows the polytropic equation up to state 2. The moment the pressure 2 is attained, exit valve opens. When the exit valve opens, the vapor inside the cylinder is removed at constant pressure. So, the system becomes an open system. Now, total work in this system is the area of this diagram 1, 2, 3 and 4. If you want to take area of this diagram, so work done during this process 1, 2, 3, 4 is the area of this diagram on PV, and the work done can be calculated as the work done during process 1 to 2 plus work done during process 2 to 3 minus work done during process or area under 4-1. So, area under 1-2 is nothing but 1 to 2 PdV, where PV raised to power n is equal to constant, because during process 1 to 2 the system behaves as a closed system. So, P is equal to C V raised to power minus n. Putting this value here, we will be getting C V raised to power minus n dV. Now, again 1 to 2 C V raised to power n minus n dV is equal to C V raised to power 1 minus n upon 1 minus n from 1 to 2. Now, C is also equal to P1 V1 raised to power n is equal to P2 V2 raised to power n. Now, if we are taking P1 V1 raised to power n here and P2 V2 raised to power n here and C goes inside, then it becomes P2 V2 power n V2 raised to power 1 minus n minus P1 V1 raised to power n and V1 raised to power 1 minus n divided by 1 minus n, and that turns out to be work under during 1 to 2, that turns out to be P2 V2 minus P1 V1 divided by 1 minus n. Because here in this process work is consumed by the system, we will take negative of this and the final expression will be, and this expression is for the work under this curve, let us say 5 and 6. So, work under 1, 2, 5, 6. This is the work done during compression from state 1 to state 2. For state 2 to state 3, is going to be P2 V2 minus V3, because V3 is 0, we can always write P2 V2. Now, we have area under this also. Now, total area minus this area will give the work done during compression, and this area is again P1 V1. Now, if we add all these 1 and 2 and subtract this one, we will be getting an expression for work for the compressor, that is P2 V2 minus P1 V1 divided by n minus 1 plus P2 V2 minus P1 V1. And the final expression is going to be n upon n minus 1 P2 V2 minus P1 V1. We can further simplify it by taking it in terms of pressure ratio, then it is going to be equal to P1 V1 P2 by P1 raised to power n minus 1 upon n minus 1. This is the work of compression for this process. But in actual practice what happens, because at this state the piston will be striking the head of the cylinder, volume is 0. So, piston will be striking the head of the cylinder, therefore, in order to avoid any damage to the head, some clearance is provided, and this volume is known as clearance volume. So, after the compression process remains same, from state 1 to state 2, but instead of reaching up to here, the stroke terminates at state 3 and some clearance is provided between the piston head and the cylinder head. Here we have compressed gas which could not go out of the compressor, so the expansion of this gas takes place. State 4 is attained, and after attaining state 4, the intake of or the suction of vapor takes place. So this is actual cycle where initially the compression takes place at the bottom dead center, then after state 2 the exit of vapor starts from the compressor, it terminates at state 3. At state 3 we have compressed vapor. This compressed vapor expands. The system behaves as a closed system up to state 4. When state 4 is attained, the suction of the inlet valve of the compressor opens and suction of vapor takes place. So in order to find work done during this process, now we have already calculated work done in this process. So if we take work done in this process minus work done in this process will give the work consumed by the compressor. So net work done for this is, let us take 5 and 6. So net work done will be area 12561 minus area 43564. Area 12561 we have already derived. And similar fashion we can find the area for this as n upon n minus 1 P1 V4 P2 by P1 raised to power n minus 1 upon n minus 1. And net work consumed by compressor during compression of vapor is going to be n upon n minus 1 P1 V1 minus V4 P2 by P1 n minus 1 upon n minus 1. So instead of having V1 in previous expression, now we have V1 minus V4. This is the actual suction volume and it is often referred as VAS, actual suction volume, because in this process only suction of vapor takes place. This process only expansion of high pressure vapor takes place and there is no suction of vapor. So if we are shifting point to this direction, less and less vapor will get sucked into the compressor. Now after this, the volumetric efficiency of the compressor is important. Now volumetric efficiency of the compressor is the ratio of actual mass of the vapor sucked divided by mass of the vapor corresponding to the swept volume of the compressor. So mass of the vapor corresponding to the swept volume of the compressor, that is Vp. So now we have two volumes. One is swept volume of the compressor Vp, that is equal to pi by 4 d square into L. D is the diameter of the cylinder and L is the stroke of the compressor. Now this Vp is equal to, here it is V1 minus V3. So mass of vapor equivalent to this volume, so mass of the vapor equivalent to actually sucked volume divided by the mass of vapor equivalent to the swept volume is volumetric efficiency. So volumetric efficiency is going to be equal to V1 minus V3 divided by, V1 minus V4 divided by V1 minus V3. Now here V1 is this is clearance volume Vc. So V1 is clearance volume plus Vp, and V4 we can take as clearance volume multiplied by P2 by P1 raised to power 1 by n. This is this expansion process. The index of compression is from state 1 to state 2 is n, and we have assumed that index of expansion is also n, however it may be different also. So this is V1 minus V4, expression for V1 minus V4, and expression for V1 minus V3 is Vp only. Now if we simplify this, we will be getting Vc by Vp plus 1 minus Vc by Vp, P2 by P1 raised to power n. Now Vc by Vp is clearance ratio of the compressor. So volumetric efficiency is equal to clearance ratio epsilon plus 1 minus epsilon P2 by P1 raised to power 1 by n, and further we can write volumetric efficiency is equal to 1 minus P2 by P1 raised to power 1 by n minus 1. Sorry, is 1 minus epsilon. If you look at this expression, if the pressure ratio is high, it is going to affect the volumetric efficiency, and volumetric efficiency will reduce. If we increase the clearance ratio, or clearance for same Vp, the volumetric efficiency of the compressor will reduce. But in any case, in a refrigeration system, approximately 5% of clearance ratio is maintained. It can go up to 7%, but minimum of 5% of clearance ratio is maintained. Regarding P2 and P1, there may be a situation when volumetric efficiency is 0. Now, if the volumetric efficiency is 0, in that case, the value of clearance ratio is going to be this is the value of clearance ratio, this is the value of pressure ratio, not clearance ratio, pressure ratio for a given clearance ratio. It means for a given compressor, because clearance volume is constant, so there is a constant clearance volume, right? Maximum pressure is constant, discharge pressure is constant, P2 is constant, Vc is constant. If we keep on reducing the P1, let us see at what stage we will be getting the volumetric efficiency is 0. So starting from P1 here, the vapor is compressed from 1 to 2, then constant pressure discharge, and then expansion takes place. So we can locate the point 1, 2, 3, 4 here. Now we reduce P1 to, let us say, somewhere here. Now in this case, what is going to happen? The point 2 will be shifted as 2 dash, point 3 is fixed because clearance volume is fixed, but during the expansion the point 4 will be shifted here. So this is going to be the modified cycle. This is state 1, this is state 1 dash. So 1 dash, 2 dash, 3, 4 dash is going to be the modified cycle. Now we keep on reducing P1. A pressure ratio will come when we will be simply compressing the vapor, and during expansion, the expansion of the vapor will occupy the entire stroke of the compressor. So this is this situation. So in order to have high value of volumetric efficiency, because it is always desired, the pressure ratio should be as minimum as possible. This clearance ratio should be as low as possible, but not lower than 5%. Normally in a single stage reciprocating compressor for vapor compression system, the pressure ratio is of the order of 4 to 5. Now this diagram I have drawn for this reciprocating compressor has not taken into account the pressure drops in the wall. The pressure drop in suction wall and discharge wall takes place because if the fluid has to flow, suppose compressor has to suck air from outside, the pressure inside the cylinder should be less than the atmospheric pressure. Otherwise, air will not be sucked into the cylinder, because for the flow of the fluid, there should be pressure drop in the direction of the fluid flow. So instead of having state 1, we will have process something like this. So here we will have Vs suction. So instead of having state 1, we are going to have state 1 dash, and state 1 dash the volume is Vs. 1 to 2 process will remain same. Now 2 to 3 process. Compressor has to push vapor out of the cylinder. Since vapor has to be pushed out of the cylinder, the pressure inside the cylinder should be more than the pressure in the pipeline. So the pressure curve will be something like this, and this is PD. So pressure will be slightly higher at the discharge. Now here in this case, if I want to have volumetric efficiency, the volumetric efficiency is going to, and this is same, Vp. Vp is up to here. So volumetric efficiency is V1 minus V4 divided by Vp. Now V1. So in order to find V1, first of all calculate Vs. Vs is equal to Vp plus Vc, suction volume. Now we assume inside the cylinder, due to ramming action, the Vs is reduced to 1 and it is a polytropic process. So V1 is equal to Vp plus Vc Ps by P1 raised to power 1 by n. Similarly for the expansion process, because expansion does not start from 3 but it starts a little higher than 3, and the V4 is, therefore V4 is PD by P1 raised to power 1 by n multiplied by Vc. So expression for volumetric efficiency in this case is going to be equal to Vp plus Vc multiplied by Ps by P1 raised to power 1 by n minus PD by P1, just a minute, minus Vc PD by P1 raised to power 1 by n, or it can be 1 by m also. This index of expansion can be different from this. So divided by Vp. So for volumetric efficiency, it is going to be 1 plus epsilon Ps by P1 raised to power 1 by n minus epsilon, this is Pd by P1 raised to power 1 by m. So this is the actual volume expression for the actual volumetric efficiency of a reciprocating compressor when we are taking into account the pressure drop across the walls. Now after finding out the volumetric efficiency of this compressor, because this expression is very helpful in analysis of vapor compression refrigeration system. because in vapor compression refrigeration system, we always require, while analyzing the vapor compression refrigeration system, we always require the volumetric efficiency of reciprocating compressor. So here I end this lecture with this, and in the next class we will start with the reverse Carnot cycle for vapor compression refrigeration system. Thank you.